When we look at a servo motor, we see the main housing with the electrical connections entering the side. In this case, the red wire is the positive voltage wire, the brown wire is the ground, and the orange wire is the pulse width modulation signal wire. These colors do vary by manufacturer. On the top, we find a small splined gear. We can connect various attachments to this to make use of the rotation. Inside the unit, we first find a number of gears, and these are supported by some bearings. On one side, we have the output, and on the other side, we have the input. The input is connected to a DC motor, which will drive the gears. This setup is known as a compound gear train. The gears are arranged in this way to ensure a compact design. The motor has a high rotational speed but a low torque, so the gears help convert this into a low speed but high torque output. In this example, there is an 11-tooth pinion gear on the motor. This connects to a 61-tooth gear, which is directly joined to a 12-tooth gear. This connects to a 48-tooth gear, which is directly connected to a 13-tooth gear. This connects to a 47-tooth gear, which is joined to a 13-tooth gear. And this connects to the final gear, which has 42 teeth. So, for this example, using some arbitrary numbers, if the input was 259 RPM with 1 Nm of torque, then the output would be 1 RPM but 259 Nm of torque. Therefore, we have converted high-speed, low torque into low-speed, high torque. There are losses which I've purposely ignored for this example. We have covered how to calculate this in our previous video on gear trains. Do check that out, links down below. The DC motor is connected to a small circuit board inside the unit. This controls the rotation of the motor as well as the direction of rotation. Also connected to the circuit board is a potentiometer. This connects to the output gear of the servo. This is just a variable resistor. As the final gear rotates, it rotates the potentiometer, which changes the resistance, and the circuit board reads this to know the position of the output. Let's see how this works. But first, where have you seen these motors used, or what would you use them for? Let me know in the comment section down below. A controller sends a signal to the servo motor, which determines which position it should rotate to. The controller could be something like an Arduino, or even a simple servo tester. This is a pulse width modulation signal, which means it sends pulses of voltage down the wire. The width of the pulse can be varied. It's similar to if we pressed a switch to turn a light on and off. The longer we press the switch, the longer the pulse of electricity. These pulses are sent every 20 milliseconds, so we have around 50 pulses per second, or 50 Hz. We can use an oscilloscope to see these pulses. For example, this is the signal sent by an Arduino, and this is the signal sent from the servo tester. The width of the pulse determines the position of the servo. If we send a wide pulse, the servo moves to the left. If we send a small pulse, it rotates to the right. We can move to any position between these 2 points by simply changing the width of the pulse. As long as the pulse remains the same, the motor will hold its position. As soon as there is a change, the servo motor moves. We can see here that when I rotate the dial on the servo tester, it's changing the width of the pulse, and the servo motor's position changes to align with this signal. As I increase the voltage for the power supply, the height of the pulse also changes, but the position of the motor remains the same. If we use an Arduino board, we can run a program to control the position, or we can even use a potentiometer to control the position manually ourselves. We will learn how to build this later on in the video. The signal enters the servo's circuit board and is converted to a voltage. It passes through a comparator and then to a motor driver. The motor driver controls the rotation of the DC motor. It uses an internal H-bridge circuit to control the direction of rotation, either clockwise or counterclockwise, to get to the required position. This rotation causes the gears to rotate, which causes the final gear and servo arm to also rotate. Connected to the final gear is the potentiometer. You might recognize a potentiometer to look more like this. They essentially work exactly the same. The resistance increases and decreases between a minimum and a maximum value as the arm is rotated. You can see here that the multimeter is measuring the resistance, and when I turn the shaft, the resistance changes. This acts as a voltage divider. If we apply a voltage across the potentiometer, for example 5 volts, we can then measure the change in voltage due to the varying resistance. This change is proportional to its position. When the arm is turned fully to the left, the voltage is 5 volts. At the center, it is 2.5 volts, and when turned fully to the right, it is 0 volts. The potentiometer is also connected to the comparator in the internal circuit board, and the voltage is monitored to provide feedback. We know that the resistance changes between a minimum and a maximum value as the potentiometer dial is turned. So the comparator is going to compare the voltage of the potentiometer to the voltage of the controller signal. If there is a difference, then the motor will turn until the difference is close to 0. Then the servo knows it is in the correct position, so it will wait there until there is another change. Check out one of the videos on screen now to continue learning about engineering, and I'll catch you there for the next lesson. Don't forget to follow us on Facebook, Twitter, Instagram, LinkedIn, TikTok, and theengineeringmindset.com.